So when I was first learning set theory, I found it really difficult with all the proofs. I mean, I kind of like proving the different things, but I sort of, at first, it was just like, what was going on? So, sets are actually pretty simple, and the fact that they're so simple makes it so annoying to prove some things are true. It's not clear what exactly you have to do. And we'll get to that in a bit. But first of all, what is a set? Um, so a set S, um, um, what, you can say that's a collection of things, but what does that really mean? Really all it is that if you have something, let's call it X, it could be an apple, it could be the moon, and it's either in the set S or it's not. And I mean it in like a literal everyday all sense. So one of them's true, or the other one's true. Can't be both. Can't be neither. So if you have something X, it's either in the set or it's not in the set. Okay, makes sense. And that's basically it. That's all a set is. What makes the set more complicated is the stuff that we introduce to make it actually useful. So for a set to be useful, you have to know what it means for two sets to be equal. And so from what I told you, if you think about it a little bit, the most obvious way to make the sets equal would be to say the two sets are equal if they have the same things in it. Right? That makes sense. And this rule is called the axiom of extension. You better write that down if you remember it, because it's not obvious at all what extension has to do with the equal symbol. Yeah, I always thought extension meant you add more elements, but no, it just means it's equal. So here's what I mean. So here's how you write it down in symbols. So two sets X and Y are equal if and only if. So they're equal means these things and these things will mean that they're equal. So it goes both ways. So it's a definition of the axiom of an extension you could literally think of as a definition, but it's a fundamental one. So axiom of extension says that given any element, so for all X in X, we have that. So in fact, let's see. So there's two criteria. So we can do this. And first of all, X. So if X is an element of the set X, then X is also an element of the set Y. That has to be true. And if X is an element, if Y is an element of the set Y, then Y has to be an element of the set X. If these two conditions are both true, then we have X and Y are equal. So that's the axiom of extension. Okay. Okay, now we have the sets. We want to know what kind of sets there are. So first of all, we need a very basic set to start us off, to build off of and get more sets. So we want to make the most basic set we can, and this set we want to call the empty set. So this is called, well, I usually think of it as the axiom of empty sets. I'm not sure exactly what it's called, but the axiom is that an empty set exists. That's what it says. So I'll say it's the existence of the empty set axiom. And it says that there exists an empty set such that given x, it could literally be anything. We know that that for all x is not an element of the empty set. So it doesn't matter what x is, I can tell you for sure it's not in the empty set. Okay, so we have that. And one thing you can try and show, and it's not very difficult to do, is show that every empty set, all the empty sets are equal, so there's only one empty set. And if you haven't done any kind of proofs, it is pretty annoying to know how you get started. So first of all, you suppose these two are empty sets, right? And you suppose that there could be any two empty sets. And what you want to do is just show they're equal. So you know how to show they're equal. You've got the axiom extension, right? And no empty sets exist, so you've got no problem starting off. But how do you show they're equal? Because this says if x is an element of x is an element of y. But then there's no elements in either of these, right? Because of the empty set. So what do? Well, what you say is that this is vacuously true. Vacuously true. Vacuously true. You should try saying that a couple of times, you'll get it. Vacuously true. And what that means is that it's true by default because it can't possibly be false. So we say that for all x in the first set, x is in the second one, it can't be false because you can't give me an x in the first set. That's not in the second because you can't give me an x in the first place. Okay, let me just say that one more time. We know that every x, we say that every x in the empty set 1 is in the empty set 2 because there's no x in the empty set 1 that's not in the empty set 2. Okay, hopefully that made sense. And similarly, there's no x in the empty set 2 that's not in the empty set 1. And so every x in the empty set 2 is in the empty set 1. It's similar to me saying that all the elephants on my shoulder are pink, if you've heard that before, even though there's no elephants on my shoulder. So it's vacuously true, and therefore those two are equal. A proof would be me writing down everything I just said. Well, not everything, but like, you pick it up once you start getting into set theory, what exactly you should write down. I won't start writing down proofs right away, because it's a bit of a pain in the ass. But I'll do it, I swear. Okay, so what is a... So, now we have the empty set. What now? Now we want another axiom, and this is called the axiom of specification. So this axiom just says if you have a set S, in fact, the axiom of set specification actually does nothing so far. We'll come back to it in a second, and then you'll find out why. So before we make the axiom specification, we need something called a power set. So if X is a set, then the axiom of power set says that the power set of X is also a set. But that's pretty much meaningless if you don't know what a power set is, So a power set is a set such that S is an element of the power set if for all S in the set S. Sorry, if S is in the set S means that S is in set X. Okay, so this is the X. This is how a power set is defined. The axiom of the power set just says the power set exists and it's a set. Sorry, it doesn't say if. Yes, it says the power set. There is. Okay, so what it says is the power set is a set and therefore it exists. Yes. Okay. So, yeah. So the axiom says that there exists a set, the power set, such that if S is an element of the power set, then this must be true. This must be true. That if S is an element, if a little s is an element of the set S, then S is also in X, which we use to make a power set. Okay, well, it will make more sense once you see an example. So, what are the sets we have so far? Well, so far we have the empty set. So let's say the power set of that. Okay, now we want to think of all the sets, such that every element in that set is also in the empty set. Well, there's no elements in the empty set, so we're a bit stuck. But before, remember the vacuously true bit? Yep, the empty set is in the empty, and everything in the empty set is in another empty set. So, the power set of the empty set is the empty set, and there's literally nothing else that could possibly be in the power set, because any other set would have an element, right? And then not every element in that set could be possibly in the power set. And so this is it. This is the power set of the empty set. Okay, so now we've made a new set. Well, hooray! So now we have this new set. We can take the power set of this new set. I mean, why not? What's stopping us? Nothing. We've got the axiom that says that this is a set now, and we can just shove it in the power set, because it can take the power set of any set. Okay, and what's that? Well, clearly, the empty set is in here, right? Because every element in the empty set is also in here, right? It's for the same reason we said before. But then, the set containing the empty set is also in here. Now, it's less obvious why this is in here, but every element in the set containing the empty set is in this set over here, namely the empty set. Okay, now the question is there any more? Is there any more elements in the power set? And I argue there is not, right? So in each of these cases, right, we either took, so the way we constructed the sets, the elements of the power set, is we either took out elements from here or we kept them in. So you see, because every element in these sets has to be in this set, so that means we can't add any more. That means we can only take them away, right? And this is only one thing. The only things you can do is keep it in there or take it out, right? So that gives us two choices. And there's a result of those two choices. But how about if we had two things? So now we have this set over here. We can plug that into the power set. And then, in fact, this we can now guess is going to have 4 things, because we have 2 options for this, we keep it in or take it out. 2 options for this, we keep it in or take it out. When we multiply them, we get 4 different choices. So the first choice is the empty set, in which we take both out. Then we have the choice of the set containing the empty set, in which we take out the second one and keep the first. Then we have the choice of the set containing the empty set. Right? And we also have the option of this entire thing, which is the empty set and the set containing the empty set. Okay. And which gives us 4 elements. And this gives us 1. Now you might ask, is it possible for us to make a set with only 3 elements? And so far the answer is no. But if we add 1 extra axiom, we can make a set of any size we like. And here's the axiom, which I wrote down before, but I write down now. Axiom of specification. So the axiom of specification gives us some rule, and I'm going to call this rule maybe R of X. And we say that, and this can be true or false. So it's true if our X satisfies this rule. So maybe we could say that X is an orange would be the rule. Or more specifically, we could have that X is the empty set or something, right? It could be anything, any rule. We have that if, so then this is the axiom of specification, okay? If we're given this rule, which is either true or false, given an X, so it would be better perhaps to call it a proposition, right? A proposition that takes in a variable X. So maybe my name as X would be an example. Is X, where X is a variable. It's only true if I actually put my name in there. Or maybe I am something years old. Although it changes every year for some arbitrary reason. It would be correct now if I said, for example, 19. Okay, so we have this proposition P, which takes in a variable X. So the axiom of specification says that if X, so S is a set, and we have proposition P of X, then X is also a set. So in fact, the proposition, such that P of X, excellent. So as I was writing it down, I kind of lost track of what I was saying, so I'll rewrite it. So if this is a proposition and this is a set, then we can construct a set S such that with using only the elements of the set S where the proposition is true. Okay, so let's have a look at an example. an example would be, so remember when we had the set containing the empty set and the set containing, so we have the set containing the empty set and the set containing the empty set, right? You might wonder why I'm using weird sets like this. So far this is the only sets we can make. Maybe later on we'll discuss more rules for making more sets, but so far these are only sets we have. And so I'm going to use this, okay, deal with it. And I'm going to call this set S, okay. And now we want to construct a set X such that we take every element of the set S. We use only the elements of the set S where S is equal to the empty set, let's say. Okay, and then we would have this set, right? Or for example, we could make another set where we take every element that is not equal to the empty set, right? In which case we would have this set. And you can kind of see how we would make a set with only 3 elements. What we would just say is we get rid of one of these two, for example, and in that case you'd have a set with just 3 elements. Okay, and what does the axiom of specification say? It says that given a proposition, given a proposition and a set S, we can create a set X like this. And if S is a set and P is a proposition, we can create a new set X in this way. So the axiom specification says that you can create a set in this way. I think also, so the thing I'm just thinking about now is whether it says it exists or not, because we have the axiom of power sets that says that this set exists, right? Because every element in X will also be in S. So we know that this X, whatever it is in the power set of S. However, now we have the axiom specification, we know that it's a set, if that makes sense. I'm actually trying to think that through. So before we didn't know every element of the power set is a set, and now with the axiom specification, we know that every element of the power set is a set because we can make some rule to make that element, right? Although that probably needs proof. Though I can't imagine that'd be very hard to do. So that's the 4 main rules that you need to know, and with that you can make essentially a set of any size. And now you might wonder, how do we make more? Like, now we have a set of any size, what can we do? And what we can do is we can introduce something called a cardinality to each set. And so a cardinality is, so in some cases you can think of it as assigning, but it's not quite assigning a number to a set. It's more like defining a number in terms of a set. So we define 0 as the cardinality of the empty set. And we wrote it this way. So maybe you could think of it as the empty set has no elements. And we, for example, define the cardinality of the set containing the empty set as 1. And you can think of it as the set containing the empty set contains exactly one element, right? And so on. In fact, I'll just do one more example just so we know what I mean by so on. So this, for example, would give us 2, and this, for example, would give us 3. Okay, and you can see that I could it's not necessarily unique. There's more than one way, so I could construct a set with 3 elements, but let's say, but there is a rule for cardinalities, which tells us that it doesn't quite matter. So this is the main rule for cardinalities, and it says something that we'll get to later on when we know more about functions. But just as a quick, if there's a way, in fact, no, I'm not going to jump ahead. There's a lot more that we need to know to be able to define a cardinality, but essentially this is kind of what a cardinality looks like. It's a way to assign a collection of sets with a certain property. In this case, intuitively, we can see it's the size of the set to define a number. And once we have those numbers defined in that way, we can use them for certain things. For example, maybe addition or something, if that turns out to be something that we need it for, multiplication or what else. And then we can use these numbers to construct more numbers. For example, maybe we say that there is a number x such that if we add it to 2, it becomes 0, and maybe we call it -2. I mean, God forbid we come up with such a ridiculous name, but we could do that, potentially. And maybe we decide one day that there are numbers between 0 and 1, like, for example, a half, and then later on we kind of, I don't know, explode in our imagination and just think of ridiculous numbers like the square root of 2 that can't be expressed as a ratio of 2 integers, and so on. And yeah, the possibilities are endless, and this is why you should, learn set theory. So that's the end of this video.